Let's go over the 4 common number systems that you're going to be working with in Intro to Mechatronic Systems 2. The first one, decimal or base 10, which you are familiar with, binary base 2, octal base 8, and hexadecimal base 16. Base 2 binary is the one that it's used by computers or digital logic, and these base 8 and base 16 are just techniques to analyze bit patterns out of your binary numbers or reduce the information from your base 2. Let's go over decimal or base 10. Base 10 uses 10 numbers, 0 to 9. Let's use the example 492. How do I know that this is in base 10? From now on, I need to indicate the number in parentheses with the respective base, in this case base 10. And 492 can be decomposed in 4 times 100 plus 9 times 10 plus 2 times 1. What I have here is I have my inputs, the 4, the 9, and the 2. And now I have my decimal weights, the 100, the 10, and the 1. And notice that I'm using base and the respective power, 0, 1, and 2. If we understand this, now we're in good shape to go to binary numbers. For binary numbers, we have two numbers, 0 and 1. And I'm going to use this binary number as an example. Notice that I'm using base 2 over here. And I want to convert this binary number to decimal. I want to know how much is this binary number actually, what does it mean? Which number does this binary number mean? In order to do that, I'm going to apply the same technique. So I find my input, which is 11001000. I find my binary weights, so my base 2, and my power. I'm going to convert these binary weights to decimal weights because it will make my life easier. And now I'm going to assign the bit with less importance, which is going to be this one, and we call that the least significant bit, and the bit with most importance, which is this one, the most significant bit. In order to understand the MSB and LSB, we can think about dollars. If I write this number over here, which one has more weight? The 5 is most important than the 1, which is your least significant bit. Same thing applies for your binary numbers. And now I want to convert this to decimal. All I need to do is multiply my input with my decimal weight. Exactly the same thing as you did for your base 10. You do all that and you sum together and you get 200. Notice that the places where you have a 0, 0 times that decimal weight gives you a 0. So it's literally just summing where you have a 1. For your octal base 8, we have 8 numbers from 0 to 7. And I want to know which decimal weight is this octal number representing. Apply the same technique. Your input is 310. Your octal weight is your base and your power. Convert this to your decimal weights. Multiply your input with your decimal weight. Sum everything together and you get your conversion. 200 in base 10. For your hexadecimal base 16, you have 16 numbers from 0 to 15. But I want to use just one character to represent the numbers that have 2 digits over here. And that's why we're using the letters A, B, C, D, E, and F. So now I want to find the decimal value of this hexadecimal value. I do the same thing. Input C and 8. Your hexa weight, base, and power. C is 12. 12 times 16. Plus 8 times 1, and you get your 200. This table shows the numbers represented in decimal, binary, octal, and hexa. It's interesting to see that octal and hexa are using less symbols or less bits to represent exactly the same binary number. So let's see how we actually move from binary to octal and binary to hexa. And for that, let's put all the weights over here, the binary, octal, and hexa. Let's pay attention here on the base 8, on the power, that is going to change after 3 bits. And in your hexa, the power is going to change after 4 bits. Let's have this in mind. And let's see how can I convert my original example, this binary number, to octal. So my power was changing every 3 bits. That means that I'm going to group my binary numbers in sets of 3 bits. For this last one over here, I can add an extra 0, which is fine. And I get one group here, one group here, and one group here. And now to convert binary to octal, I need to convert these numbers to decimal and write them in base 8. So I'm going to use that information that I used before, your binary weights, convert to decimal weights. So I get 1, 2, 4, and 8. And now all I need to do is to convert these numbers, 0, 0, 0, multiplied by 4, 2, and 1 gives you 0. Your 0, 0, 1 multiplied by these is just the 1, so I get 1. And then I get the 0, 1, 1. So 0, 1, 1. So it's 2 plus 1 gives me 3. And that's your octal number, 3, 1, and 0. For your hexadecimal representation, you do a similar thing, but now you group the bits in sets of 4, and you get this representation over here. Now I apply the same thing. If I plug these 1, 0, 0, 1, 0, 0, 0 over here, I get 8. And if I plug this green over here, I get 8 plus 4 is 12. 12 is C, and that's your number in hexadecimal.